Hello students, in this video we begin our discussion of vector identities using the del operator and the Kronecker basis. So let's let delta hat 1, delta hat 2, delta hat 3 be the standard basis. So they're just I, j, and k, but we use 1, 2, and 3 as indices for convenience, right? And then we define the del operator as follows. Del is simply just the sum over I of the partial with respect to xi delta I hat. Now this del operator allows us to compute gradients, divergence, curl. So let's see how that helps us. So using this operator, we can define what can we define? We can define gradient, divergence, and curl using this operator. Okay, how do we do that? So if f is a scalar function, then this implies that del f will be the sum over I of what? Well, I'm going to take this f, I'm going to put f into the partial derivative. So I'm going to have partial f partial xi delta I hat. And this is the gradient. This is the gradient of f. And imagine with our standard definition, we think of, remember that delta 1 is what? Delta 1 is I, delta 2 is j, delta 3 is k. So this exactly is equal to what? In our standard notation, this is just fx, fy, fz. So it coincides with our standard notation. This notation will help us with vector identities though. Now if v is a vector field, so if v is a vector field, then this implies what? Then I'm going to define del dot v to be what? Well, let's think about what this would be. This would be the sum over I of partial xi delta I hat. Then I'm going to dot this whole thing with what? I'm going to dot this whole thing with the sum over j of what? Of vj delta j hat. So what I'll have over here is I'm going to have the sum over I and j, of just partial vj partial xi, and then delta I dot delta j is delta ij. And so when I have a delta ij in my summation, I can replace all the i's with j's. So this is going to be equal to what? Just the sum over I of partial vi partial xi. And that's our standard definition of divergence. So this over here is just the divergence. By definition, this is just divergence of the vector field v. Del dot v is the divergence of the vector field v. Okay, so in our standard basis, what will this be? This is going to be v1 with respect to x plus v2 with respect to y plus v3 with respect to z. So we see that this one sort of expression over here captures all three terms of my divergence. It's even more useful for curl. Let's see curl. So again, v is a vector field. What would del cross v look like? This would look like what? Well, I have the expressions of del. So what we're going to have for remember how we cross two vectors, we have the sum over epsilon I, j, k of the combination of the terms of ai, bj, delta k hat. So we'll have over here is we're going to have the sum over what? The sum over I, j, and k, epsilon I, j, k, partial vj, because that's the second term over here, partial vj, partial xi, delta k hat. And we can check going through term by term that this coincides with our ordinary definition of curl. So this is exactly just the ordinary definition of curl of v, which we know from the ordinary notation, right? And so of course, how do we think about this? Well, of course, what's del? This is really the sum of what? Of partial xi, delta I hat. And I would cross that with what? I would cross that with the sum over j, that's the sum over I, of what? Of vj delta j hat. And so I'll have this term over here, and this term over here will give me my what? My vj xi, and then delta I cross delta j, if we recall, recall that delta I cross delta J was the sum over ijk of what? Of epsilon ijk delta k hat, and that's where we get this epsilon ijk delta k hat. In future videos, we'll see how these relationships can be used to prove vector identities with great ease. Thank you very much.